Hello, how you doing? All right, so we're here to look at Chapter 2 of CCNA 4, which is point-to-point connections. So we're going to talk about point-to-point connections, of course, and so a couple of protocols. And so HDLC, which is high-level data link control, that's been around for a very long time. A slightly newer protocol is P, or point-to-point protocol. And so it's actually sort of like version 2 of HDLC, actually, but with a fair bit more functionality. We're going to look at implementing P, and we'll also look at troubleshooting P. Okay, so point-to-point serial overview. So, a WAN is owned by a service provider, and a LAN is typically owned by an organization. Point-to-point connections connect LANs to service provider WANs, and they connect LAN segments together. A LAN to WAN point-to-point connection is referred to as a serial connection or leased line connection. Lines are leased from a carrier, so be that your telco or ISP or whoever it might be, and companies pay for a continuous connection between two remote sites, and the line is continuously active and available. Sorry about that. Okay, so serial compared to parallel ports. So serial communication basically means one bit after the next, and so it's a series, hence the name serial, of ones and zeros basically. So equivalent to a pipe, only wide enough to fit one ball at a time. Multiple balls can go into the pipe, but only one at a time, and they only have one exit point at the other end of the pipe, and so that's a serial connection. So yeah, the bits follow one another down that cable, as opposed to parallel, which means you actually have multiple cables, and so you can send multiple bits at the same time. So as it says, bits are transmitted simultaneously over multiple wires with parallel communications. So you can send 1 byte or 8 bits in the time that a serial connection sends a single bit. At one time, most PCs included both serial and parallel ports. Parallel ports were used to connect printers, computers, and other devices that required relatively high bandwidth. So on most PCs, parallel ports and RS-232 serial ports have been replaced by the higher speed USB or universal serial bus interfaces. Now, it depends on if you've got legacy ports on the back of your PC, basically. And so from this slide, you would look at it and think, well, parallel sounds better. But the problem with the parallel, much the same as when we've spoken about when we transmit data through Ethernet cables, is that they can actually affect one another. And so the distances possible with a parallel port are much shorter on a parallel compared to a serial connection. So serial cables can be quite long, parallel cables cannot. And so that is a limitation of the parallel connections or ports. Okay, so a point-to-point link is used when permanent dedicated connections are required. It provides a single pre-established WAN communications path. The path goes from the customer premises through the provider network to a remote destination, as shown in the figure. So basically, in this case, you've got a New York office and a London office, and so we've got a router at each site. We've actually got basically they're like a modem that will translate the signal from a pure digital signal into whatever is required to go over the provider's network. And so, of course, there's the obligatory cloud, and so how that actually gets through the cloud is basically a matter for the telco, and that's it. So you can connect two geographically distant sites, such as corporate office in New York and a regional office in London. It's not limited to connections that cross land, so you can have undersea fiber optics as well, usually more expensive than shared services. Constant availability is essential for some applications such as VoIP or video over IP. So we're basically talking about a leased line, and so you pay for it 24/7. It is yours to use. Not a cheap way to go, though. Okay, so when it comes to bandwidth with serial links, it's really how much money do you have and how much are you willing to spend. And so basically bandwidth, of course, is the rate at which data is transferred over that communication length. Carrier technology will dictate how much bandwidth is available. And so North America and Japan use the T-carrier spec, while most other countries use the European or E-carrier spec. And there's also the US optical carrier as well. So OC transmission rates are a set of standardized specifications for the transmission of digital signals carried on SONET fiber optic networks. In North America, expressed as digital signal level number, DS0, DS1, etc., refers to the rate and format of the signal. So most fundamental line speed is 64 kilobits a second, or DS0. 24 DS0s can be bundled to get a DS1 line, which is T1. 28 DS1s can be bundled to get a DS3 or T3 line. And so the 56, of course, 56K was the maximum speed possible on the old modems. 64K is typically what is used in ISDN. And then, of course, bundling them together, you can get T1 or E1. And then, of course, all the way up. And so J1, which I'm from memory is Japanese, and of course it's the same as the T's. And so so T1 is 1.544 megabits a second. E1 is 2 megabits per second, and so but E3 is not as fast as T3. So and then of course there's all the OC standards. So WAN encapsulation protocols. So data encapsulation into frames before crossing the WAN link and must be configured for the appropriate layer 2 protocol. So choice of protocol depends on the WAN technology and the communicating equipment. WAN protocols, HDLC and TPP are the focus of this course. And so HDLC, as I said, is high-level data link control. It's a default encapsulation on Cisco routers on point-to-point connections, dedicated links and circuit switch connections when the link uses two Cisco devices. Now, HDLC is a standard, but it sort of had some missing features, and so many vendors have sort of added to it, and of course that makes it non-standard, Cisco included. And so HDLC on a Cisco device won't talk to HDLC on anyone else's devices. And so to fix that problem, TPP was developed. And so point-to-point protocol, and provides router-to-router and host-to-network connections over synchronous and asynchronous circuits, has built-in security mechanisms such as PAP and CHAP. And so TPP has extra functionality compared to HDLC. Now, there were some other protocols about. So SLIP, or Serial Link Internet Protocol, was replaced by TPP. That was actually how you used to dial up back in the dark ages, was using SLIP. It was fairly slow. X25, I think, comes from back in the 60s or maybe 70s. And that is basically, you can buy virtual circuits using X25. X25, because it's an old protocol, had industrial strength error recovery built into it, which was really good when we had lots of errors in network transmission. Of course, these days we don't have so many errors, and so it's just extra overhead for not a great deal of benefit. And so frame relay is very similar to X25, except it's a lot more streamlined, and so you get better bandwidth out of it. And so frame relay, again, you do virtual circuits, and so you can have permanent or switch virtual circuits, but switch virtual circuits weren't very common. And then there's ATM, which is asynchronous transfer mode. It's an international standard for cell relay as opposed to frames, cells, and so in which devices send multiple service types such as voice, video, and data in fixed length 53-byte cells. It takes advantage of high-speed transmission media such as E3, SONET, and T3, and also ASICs, or application-specific integrated circuits. And so all of the switching could be done in hardware, no software intervention required. Very efficient for that, but the downside is it's really good for voice and videos, but that tiny little cell, 53 byte, and you only get 48 byte payload, is tiny compared to, a 1500 byte frame that you can send with frame relay or triple P or whatever it might be. And so it makes it less efficient for data. Very good for voice and video, not as good for data. So HDLC has been around for a long time. And so as you can see, this is the standardized HDLC frame. And so you had a flag that started it, any addressing that was required, which was pretty well not much used, any control data, and then, any control sort of information, and then you had the data field, which of course was variable in size. Then there's a frame check sequence and the end of frame flag. Now, as you can see, Cisco added something to it because with HDLC, it couldn't actually identify which layer 3 protocol used it, and so they added an extra field in there for which layer 3 protocol is using it. And so it gave functionality, so you could have HDLC with multiple layer 3 protocols. But as I said earlier, it made it non-standard, and so if you've got a Cisco device, it will not be able to talk to any other vendor's HDLC device. So HDLC is a standard, but sadly, not many companies follow the standard because it was missing some functionality. So now, if you are using a serial interface on a Cisco router, it will be using HDLC by default. But yeah, if you need to hook it into some other vendor's equipment, you will need to change it to triple P. So the protocol field makes it possible for a single serial link to accommodate multiple network layer protocols. So, this was done back in the 90s, I think, where they added the extra field. And so there was IP, there was IPX, there was AppleTalk, there was all these protocols, and so it needed that extra functionality. Of course, these days, the only one of those that remains is IP, pretty much. But of course, these days, there's IPv4 and there's IPv6, and so again, it would need a protocol field for that as well. And so, yeah. So HDLC, without that add-on, is not much use to you. So, yeah. So anyway, so how do we configure HDLC? So if you do nothing out of the box, it will be using HDLC. So if you do show interface serial 000, it will actually say the encapsulation is HDLC. You don't really need to do this command, encapsulation HDLC. The only time you'd need to do that would be if it had been set to something else, and so you could then set it back to HDLC. So it's point-to-point and on less lines between Cisco devices. If connecting non-Cisco devices, you need to use triple P. If the default encapsulation method has been changed, use encapsulation HDLC to re-enable HDLC. So when you do show interface, S000, as I said, it will actually tell you that the encapsulation is HDLC. And so, yeah, that's pretty much all you need to do. It will be working if you have it. And so, of course, as long as it says the line protocol is up, that means that HDLC layer 2 is happy. Okay, so troubleshooting a serial interface. And so serial interface issues associated with state and how to troubleshoot the issue. So if the serial, so of course the name of the serial port means this is the physical layer. So physical layer is good and the line protocol is good, so it's data link layer, there's no problems. If serial X is down, line protocol is down, well, serial X of course means that's the physical layer. If that's not working, data link layer was never going to work. And so basically you've got to figure out what's wrong with the physical layer. And so basically it hasn't been able to detect a carrier signal as one possible problem, or the WAN carrier service provider has a problem, or you have faulty cabling, or you have faulty hardware. And so if you have serial X is up but the line protocol is down, you basically need to fault find what's wrong with the layer 2 protocol, and so whether the other end of the link is a different protocol, that's going to cause that. And you can also have problems with things like clock rates and other such things like that. And so it does depend on the carrier service unit or data service unit, CSU/DSU. And so, yeah, whether that's got a problem, that's probably where it would be. Okay, now you can actually use the show controllers command, and that output that indicates the state of the interface channels and whether a cable is attached to the interface. In the figure, the serial interface 000 has a V35 DCE cable attached, and so this is what at least us people will use it most often for. Is if you've got a cable plugged in, you don't know which end is the DCE end, which is the DTE end. You can actually look at it in the third line. It will tell you DCE or DTE, or it would say no cable connected. Okay, so triple P. So as I said, HDLC, standardized HDLC has that problem and it can't support more than one layer 3 protocol. And so triple P has a fix for that. And so at least triple P is standardized and supports it in that fashion. And so that is certainly a good progression. And so when it comes to triple P, it is actually based on HDLC. If you look at the encapsulation, it's very closely related. Now, you should use triple P if you're connecting to a non-Cisco router. And so triple P encapsulates data frames for transmission over layer 2 physical links. Triple P establishes a direct connection using serial cables, phone lines, trunk links, cellular telephones, specialized radio links, and fiber optic links. And so there's 3 main components of triple P. So there's HDLC-like framing for transporting multi-protocol packets over point-to-point links. There is an extensible link control protocol for establishing, configuring, and testing the data link connection. And there was a network control protocol for establishing, configuring different network layer protocols. And so, of course, these days, the major options are IPv4 and IPv6. So it includes many features not available HDLC. So you can actually do link quality management with triple P, and it monitors the quality of the link and can be configured with the interface command triple P quality and then a percentage. If the error percentage falls below the configured threshold, the link is taken down and packets are rerouted or dropped. And so, of course, triple P also includes authentication. So there's PAP and CHAP. So CHAP is the more secure of the options there. So triple P has its own layers within it, and so basically NCP network control protocol is basically the interface between it and the layers above, and so there's actually a control protocol for each layer 3 protocol that it uses, and then basically all of the purely layer 2 stuff is done by the LCP, authentication, other options, and link control protocol. And so the figure maps the layered architecture of triple P against the OSI model. Triple P and OSI share the same physical layer, but triple P distributes the function of LCP and NCP differently. Triple P requires a full duplex circuit, either dedicated or switched, that can operate in an asynchronous or synchronous bit serial mode. Most of the work done by triple P happens at the data link and network layers by LCP and NCPs. So the link control protocol, so bottom half of triple P. So it functions within the data link layer and has a role in establishing, configuring, and testing data link connections. So it establishes that point-to-point link. It also negotiates and sets up control options on the WAN data link, which are handled by the NCPs. After the link is established, triple P also uses LCP to agree automatically on the encapsulation formats such as authentication, compression, and error detection. Now, the NCP, or Network Control Protocol, permits multiple network layer protocols to operate on the same communications link. For every network layer protocol used, triple P uses a separate NCP. As shown in the figure, IP version 4 uses IP control protocol, and then there's IPv6 control protocol. NCPs include functional fields containing standardized codes to indicate the network layer protocol that TPP encapsulates. And so a value of 8021 means it's IPv4. If it's 8057, it means it's IPv6. Okay, so the frame structure. And so basically, if we think back to that previous slide when we looked at the HDLC setup, we have a start and stop flag at the start and stop of the frame, and they actually use the same bit sequence of 0, 6 ones, and a 0. That is deemed to be the flag. And so that is consistent. Addressing a single byte that contains the binary sequence of all ones, basically, because it's a point-to-point link. There's only 2 hosts. Really, addressing is irrelevant. And then there's a control, which is a single byte that contains the binary sequence of 6 zeros and 2 ones, which calls for transmission of user data in an unsequenced frame. And then there's the protocol, which is 2 bytes that identify the protocol encapsulated in the information field of the frame. And so, again, that's much like that Cisco version of the frame format. And then you have the data area, which of course is a variable sized data frame to moving data across the link. And then there's a frame check sequence, which of course is how you do error checking for the data that's crossed the link. Make sure there's been no errors in transmission. Okay, so how does a TPP session get established? And so for phase 1 is link establishment and configuration negotiation. And so before it exchanges any network layer datagrams, such as IP, the LCP must first open the connection and negotiate configuration options. This phase is complete when the receiving router sends a configuration acknowledgement frame back to the router initiating the connection. And then phase 2, there is a link quality determination, which is optional. And so it tests the link to determine whether the link quality is sufficient to bring up the network layer protocol. So is it working well enough to bother? And then phase 3 is the network layer protocol configuration negotiation. So after LCP is finished, phase 2, the appropriate NCP can separately configure the network layer protocols and bring them up and take them down at any time. The LCP closes the link. It informs the network layer protocol so they can take appropriate action. Okay, so LCP operation includes provisions for 3 classes of LCP frames, and so there's link establishment, link maintenance, and link termination. And so basically, during link establishment, the LCP opens the connection and negotiates the configuration parameters. The link establishment process starts the initiating device sending starts with the initiating device sending a configure request frame to the responder. And then the responder processes that request. If the options are not acceptable or not recognized, the responder sends a configure negative acknowledgement or configure reject message. If the options are acceptable, the responder responds with a configure acknowledgement message and the process moves onto the authentication stage. And then the operation of the link is handed over to the NCP. So basically, there are configuration parameters on both ends. If they are compatible, you'll get a configure acknowledgement. If they're incompatible, you'll get either a negative acknowledgement or a reject. When NCP has completed all necessary configurations, including validating authentication, the line is available for data transfer. During the exchange of data, LCP transitions into link maintenance mode. During link maintenance, LCP can use messages to provide feedback and test the link. And so there are echo request, echo reply, and discard request frames. And so they're used for testing the link. And so code reject and protocol reject, these frame types provide feedback when one device receives an invalid frame. The sending device will resend the packet or frame, I suppose. Okay, so link termination. After the transfer of data at the network layer completes, the LCP terminates the link. NCP only terminates the network layer and NCP link. The link remains open until the LCP terminates it. Triple P can terminate the link at any time because of the loss of the carrier, authentication failure, link quality failure, the expiration of an idle period timer, or the administrative closing of the link. LCP closes the link by exchanging terminate packets. And so device initiating the shutdown sends a terminate request. The other device replies with a terminate acknowledgement. Okay, so options. And so we have mentioned them briefly. So there's either PAP or CHAP, which is Password Authentication Protocol, or Challenge Handshake Authentication Protocol. And so CHAP is the better one because there's encryption. And also it's managed by the dialed entity as opposed to the dialing. So you can compress data so to improve your bandwidth across the link. And then multi-link basically means you can bundle more than one link but treat them as one. And so it's a bit like what we did with in CCNA 3 with Ether channel basically, but this is of course with data WAN links. Okay, so NCP explained. After LCP has established a link, the routers exchange IPCP messages, negotiating options specific to IPv4. IPCP is responsible for configuring, enabling, and disabling IPv4 modules on both ends of the link. And so IPCP negotiates two options. And so compression, so it allows devices to negotiate an algorithm to compress TCP and IP headers and save bandwidth. And also IPv4 addressing allows the initiating device to specify an IPv4 address to use for routing IP over the TCP link, or to request an IPv4 address for the responder. After the NCP process is complete, the link goes into an open state and LCP takes over again in the link maintenance phase. Okay, so how do we implement? And so basically you've got to think about what options you want to use. So with compression, the two compression protocols available in Cisco routers are Stacker and Predictor. And so with error detection, it identifies fault conditions. The quality and magic number options help ensure a reliable loop-free data link. And there's also TCP callback is used to enhance security. With this LCP option, a Cisco router can act as a callback client or a callback server. So basically you can ask for it to call you back, and it has to be a registered phone number. And so that's a good way of having some security. So not just anyone can dial in. Also, it's good for billing. So you might have a bulk deal for the line that the router is connected to, and you don't have to pay for that when maybe someone's at a hotel dialing in remotely. Doesn't happen much these days though. So basically, basic configuration for TCP is encapsulation TCP in the serial interface. So of course you need an IP address, but by default encapsulation is HDLC. If you do encapsulation TCP, both ends, it will be TCP. And so you'll actually get different information. You will get that different information on the show interfaces. Now you can do compress predictor, and that will, or stacker, of course. And so, of course, it's a software compression process, and so it may not necessarily improve performance. Depends on how much. Well, basically, it's going to busy up your CPU on your router. So if it's a bit busy already, it might slow things down. Okay, and so then there's the quality percentage. So with quality percentage, Commander ensures that the link meets the set quality requirement, otherwise the link closes down. And so in this example, we've got TCP quality 80. And so basically, as long as the link is 80% reliable, it will stay up. And then multi-link. And so, of course, with multi-link, you need to have multiple interfaces that you link together. And then you need to create a virtual interface, which then is what layer 3 refers to, and then joins them all together. And so you make these all a member You do triple P multi-link to say that I want to do that, and then say they belong to group 1. And so these interfaces belong to group 1, and this is your interface multi-link 1. And so that's basically the interface you'll deal with afterwards. Okay, so how do we verify triple P configuration? So encapsulation triple P. An LCP, link control protocol, says it's open. And so basically from here, then it also tells you what NCPs are running. And so IPCP, IPv6 CP, CCP, now CDP is Cisco Discovery Protocol. I'm not sure what CCP is, but anyway. So basically, so we've got IPv4 and IPv6 and CDP running across that link. And of course, it's up and up. So here we're doing show triple P multi-link. You can actually have a look what it is. And so bundle name R4. And so basically you can see that you've got 2 member links active. So serial 011 and serial 010. All right, so into authentication. So as I said, there is 2 options, PAP and CHAP, and CHAP is the better one. So PAP is a very basic 2-way process with no encryption. The username and password are sent in plain text. If it is accepted, the connection is allowed. And with CHAP is more secure than PAP. It involves a 3-way exchange of a shared secret. So the authentication phase of a triple P session is optional. If used, the peer is authenticated after LCP establishes a link and chooses the authentication protocol. Authentication takes place before the network layer protocol configuration phase starts. And so basically with PAP, what they're saying is this remote router is hooking into the central router, and it also sends its username and password in plain. And then it'll either be accepted or rejected. Now, remote router is still connecting into the central site router, but as you can see, it's actually the central site router that handles the authentication process. So it controls all of them. Like this one here, the remote router actually started it by sending it, and so brute forcing works easier in PAP than it does with CHAP, that's for sure. So basically here, the central site challenges the zone, hey, authenticate yourself. And then they will send the details, and then it will either be accepted or rejected. And so they can't just keep hammering away, because it won't happen unless there's been a challenge. So basically, also, as you can see, it is hashed. And so it makes it a lot more secure. All right, so how do we do authentication with PAP? So note, PAP is not a strong authentication protocol. Using PAP, passwords are sent across the link in plain text. There is no protection from playback or repeated trial and error attacks. Completing PAP, initiating PAP, R1 sends its PAP username and password to R3. And then completing it, R3 evaluates the username and password against its local database. If it matches, it accepts the connection. If not, it rejects the connection. So this is pretty much the only thing the router does. The central one is it just accepts or rejects. That's all it does. With challenge handshake, there's more to the process. So, of course, initially the remote router is the one that normally dials into the central router. But of course, because there's authentication, it's the central router that controls the authentication process. So R3 initiates a 3-way handshake and sends a challenge message to R1. The remote node responds with a value that is calculated using a 1-way hash function. And so the local router checks the response against its own calculation of the expected hash value. If the values match, the initiating node acknowledges the authentication. Note, CHAP conducts periodic challenges to make sure that the remote node still has the valid password value. So how do we configure that? So there's a command, triple P authentication, and then you have options. And so you can specify just one, be that CHAP or PAP, or you can specify both, but in which order. And so if you do CHAP first, then PAP, it means that CHAP will be the one that will be attempted first. If you have PAP first, PAP is the one that will be attempted first. And so that order is important. Yeah, so of course, don't think we'll be using 2 in any of our labs, but anyway. All right, so here's an example, and so of PAP, and so you need to create a local database, of course, and so of course this is on R1, so we actually need to create a username for R2 with its password. And so here you can actually set PPP sent username R2 and password. I think that's secure. It's pretty fuzzy for me, but anyway. So let's just say it is. And of course, on this router, we've got a username for R1 and again, secure. And so sent username R1 and password secure. And so of course, it's PPP authentication PAP, and then you have to configure the sent username and password. Now with CHAP, you need to create the corresponding usernames. So on R2, you need to create one for R1, and R1, you need to create one for R2. But PPP authentication CHAP is normally all you need to do. Now, the CHAP host name on the other router must match the username on the other router has configured. The password must also match. It occurs on link establishment and can be repeated. Okay, so how do we troubleshoot WAN connectivity? So you can actually debug PPP and a whole pile of things. And so basically debug PPP packet, negotiation, errors, authentication, compression, or CBCP. And so of course packet is every time there's a packet sent or received. Negotiation is basically the LCP stuff. Error is whenever there are errors. Authentication, of course, is whenever there's authentication going on. Compression tells you, when compression is going on. And CBCP displays protocol errors and statistics associated with PPP negotiations using Microsoft callback control. Okay, so the debug command must not be used as a monitoring tool. It's meant to be used for a short period of time for troubleshooting. It can consume a significant amount of resources, especially debug PPP packet. That would take a lot of resources. So your debugging can be fraught with danger, but short term, by all means, just don't leave it on. Undebug all afterwards. Okay, so debug PPP packet, as it says, shows you everything. Negotiation shows you just when it's negotiating stuff. PPP error, whenever there's errors. I use this regularly, especially when we're doing practical tests. Debug PPP authentication. So I'll actually turn that on, then I'll turn on the interface and see what happens. And so as you can see, there's challenge, response, success, and failure. Okay, so that's the end of the chapter. So we've looked at configuring HDLC encapsulation. Can be do nothing, or it can be do a fair bit. You can explain how PPP operates across a point-to-point serial link. We've looked at how to configure PPP, and we've also looked at how to troubleshoot PPP. Okay, so there's the logo. So that's the end of the chapter. There will be a demo video coming. Have a nice day. See you next time.